Hello there, and welcome. I'm so glad you made it here. Maybe your day has been heavy, or maybe your thoughts just needed a quiet place to land. Whatever brought you tonight, it's enough. There's nothing left to do but rest. Let the tension melt from your jaw. Let your breathing grow long and soft. Let your thoughts stretch out like shadows under distant suns. Because tonight, we're going to drift beyond our solar system, past the familiar planets and moons, into a galaxy full of alien worlds, real planets, orbiting distant stars, some warm and stormy, some frozen and forgotten, some covered in vapor, others wrapped in fire, worlds that spin too fast, or not at all, worlds with two suns, or none. We won't rush. We'll float from one strange fact to the next, like travelers gliding through gravity's quiet river. This isn't a list of trivia. It's a journey. 100 truths about exoplanets, told softly and slowly, each one more improbable than the last. You'll sleep when you're ready. Until then, take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. For a long time, we believed planets were rare. The stars filled our skies, fixed and bright, and our imaginations wandered among them. But the idea of worlds beyond our own was once just poetry. Ancient, impossible, and unprovable. Telescopes showed us the planets in our own solar system, but everything beyond remained a glittering guess. We thought, perhaps, that planets were flukes, lucky results of just the right dust, in just the right swirl, at just the right time. Maybe they happened occasionally, but certainly not often. Even as late as the 1,990 seconds, the official count of known planets beyond our solar system was 0. But the sky had other plans. Quietly, over decades, evidence began to build. Not photographs, those would come later, but tiny wobbles in starlight. Minuscule shifts in the way a star moved, or the way its light dimmed, again and again, in a perfect rhythm, as if something were pulling it, or passing in front of it. Something massive, something orbiting. The first confirmed planet around a sun-like star was discovered in 1995, and it was nothing like Earth. A gas giant orbiting scorchingly close to its star. So close it completed a year in just over 4 days. It shouldn't have been there, but it was. And once we saw one, we knew how to look for more. Now, we know of thousands. Over 5,000 confirmed as of today, with thousands more unconfirmed but likely. Each one its own world. Each with a different mass, a different sky, a different story. We've found planets that orbit 2 stars, like the scenes from old science fiction. Planets where it rains glass sideways, where the clouds are made of vaporized metals, where the wind never stops and the heat never fades. We've found small rocky planets like Earth and giant gas worlds bigger than Jupiter. Some orbit close in, some drift far out. Some are alone, some are part of crowded families. And that's just the beginning. The deeper truth is that planets aren't just common, they're inevitable. Nearly every star we study seems to have them. Some stars have 1 or 2. Others have entire systems, packed with tightly orbiting bodies whirling like clockwork. The galaxy, it turns out, is not just a sea of stars, it's a sea of worlds. The Milky Way alone may hold over 100 billion planets, maybe more. Some estimates suggest there could be trillions. Trillions of unique landscapes, unique skies, unique gravitational pulls. Trillions of places where wind moves differently, where time feels slower or faster, where sunrise and sunset don't mean what they mean here. Trillions of orbits around hundreds of billions of stars, and we've only just learned how to listen. For centuries, our skies told a small story. We looked up and saw 8 planets, 9 for a time. Each a known name, a studied path, a familiar neighbor. We memorized their order, imagined their surfaces, named their moons. But now, the story has grown wider. Now we know that what we once thought of as rare may be the rule. Earth is not a pearl in a dark sea. It is one light in a sky full of flickers. Some warm, some cold, some dead, some just beginning. It changes something in you when you realize that. When you really feel the numbers, not just in your mind, but in your bones. Every star you've ever seen may have planets. Every pinprick of light, even the faint ones, especially the faint ones. And some stars, hidden behind dust or too dim to spot without powerful instruments, are orbited by entire planetary systems we've never glimpsed. The sky is crowded, not empty, dense, not sparse. But it doesn't feel that way. It feels still. It feels calm. It's only when we look carefully, really look, that we see the motion underneath. Even the methods we use to detect planets are indirect. We're not looking at the planets themselves, not usually. We're watching their effect on the stars they orbit. A tiny dimming of light, a small shift in velocity, like watching a candle flicker and guessing that something passed in front of it, like listening to the way a bell rings and noticing the echo is off, just slightly, just enough to mean something. Most of the exoplanets we know were not seen. They were inferred, pulled from data, coaxed from patterns, teased out from noise, found in silence. And yet, despite these limitations, the numbers keep growing. Every new telescope adds hundreds more. Every improved model finds another corner to search. We're no longer asking if planets are out there. We're asking what kinds. We're asking how many are small, how many have atmospheres, how many might have water, how many are Earth-like. And even then, we're realizing Earth-like is a narrow idea, a story we tell ourselves to feel familiar. In truth, most worlds won't be like Earth. Some will be far stranger. And that strangeness doesn't mean lifeless. It just means different. When you sit with the numbers long enough, the scale becomes dizzying. You start to wonder not just what's out there, but who. Not in a science fiction way, but in a quiet, mathematical way. When there are trillions of planets, the odds begin to lean toward company. Not proof, not certainty, just a leaning, a soft tilt in the probabilities. Life may not be rare. Intelligence may not be rare. What might be rare is time, the overlap, the coincidence of now. There are planets out there older than Earth by billions of years, worlds that had head starts, that formed before our sun was even a cloud. And there are new planets forming right now, around stars just beginning to shine, planets that don't yet have surfaces, that don't yet have names. We are somewhere in between, middle-aged, modest, and barely aware. We are the newcomers, only just lifting the curtain. All of this from watching shadows, listening for wobbles. All of this from quiet data points, compiled and cross-checked and revisited again and again. We haven't even seen most of what's out there. But the patterns are clear. The numbers don't lie. The galaxy is full of planets, overflowing with them. Not rare, not precious, not unique. And somehow, that makes everything feel more precious, more beautiful. We are not alone in orbit, not even close. We are surrounded, bathed in planetary possibility. The sky is not just a map of stars, it is a story of worlds, and we are only on the first page. The story of the first exoplanet does not begin with a telescope, or with a photograph, or even with the hope of discovery. It begins with something unexpected, an irregularity, a rhythm that didn't match, a cosmic heartbeat that skipped, then fluttered, then settled into a pattern no one had predicted. It was 1992. Astronomers Alexander Wolszczan and Dale Frail were studying a pulsar named PSR B1257+12, a dense stellar remnant spinning hundreds of times per second, emitting radio waves like a lighthouse in the dark. Pulsars are not quiet stars. They are collapsed cores of massive suns that exploded long ago, leaving behind tiny, dense, rapidly rotating corpses. They send out beams of energy with astonishing precision, and because of that regularity, they are often used like cosmic clocks. But this one wasn't ticking right. The pulses from PSRB 1257 plus 12 were arriving just slightly too early or slightly too late. The shift was tiny, just a few milliseconds. But it was real, and it repeated in a way that couldn't be ignored. Something, it seemed, was tugging on the pulsar, something massive enough to affect its motion, not a companion star, not a comet, something smaller, lighter, orbiting with a steady gravitational pull. A planet. It didn't make sense. No one had expected to find planets around a pulsar. These are not the kinds of stars that should have solar systems. They are born in violent explosions, supernovae so intense they blast away nearby material and leave chaos behind. How could anything survive that? And yet, there it was. Not just one planet, but two, later confirmed, orbiting the remnants of a dead star. Small rocky bodies, comparable in size to Earth, caught in orbit around the collapsed core of something that had once been a sun. It was the first time humanity had confirmed the existence of a planet beyond our solar system. And it wasn't around a normal, stable star like our own. It was around a stellar ghost. A place of radiation, silence, and echoes. The first exoplanet was not a warm, water-rich twin of Earth. It was something far stranger, and its discovery changed everything. We like to think of science as linear, as methodical, but some of the most important discoveries don't come from looking in the right place. They come from looking at the wrong place and refusing to look away. That's what happened here. No one was trying to find a planet. They were studying pulsars, neutron stars, and the fine structure of radio pulses. And yet, what they found was a new kind of world, a new category of existence, not theoretical, not imagined, real. That first discovery rewired the imagination of astronomy. If planets could survive or reform after a supernova, then they could be anywhere, around any kind of star, in any kind of system. The universe, it turned out, was more forgiving, more creative, more chaotic than we had believed. Planets did not need ideal conditions. They did not require order. They could emerge from disaster. There are theories about how these pulsar planets came to be. One possibility is that they are survivors, fragments of larger planets that endured the explosion and fell into orbit again. Another is that they are second-generation worlds, formed afterward from the fallback debris that circled the pulsar and cooled into new planets. Either way, they are rebirths, worlds that should not be, and yet are. They orbit a star that no longer shines, and yet their presence still speaks. And this first detection wasn't done with direct sight. There was no image, no glowing dot in a photograph, just timing, just patience. The careful recording of when radio pulses arrived and how that rhythm shifted over days and weeks and years. It was a detection of motion through absence, a discovery made by listening, not looking. That lesson has stayed with astronomers ever since. Most of the exoplanets we've discovered are still unseen. We know them by their effects, by the way they dim their stars or pull them gently from side to side. We know them from starlight that flickers just a little, from orbits that stutter, from patterns that whisper something is there. The universe rarely shows us its secrets directly. It asks us to infer, to wait, to trust in noise and signal and time. What's remarkable is that this discovery didn't open a door. It opened a floodgate. Just 3 years later, in 1995, a new planet was confirmed around a main sequence star, 51 Pegasi b, a hot gas giant that orbited so close it completed a year in just over 4 days. It, too, was unlike anything in our solar system, but it wasn't alone. The years that followed brought more and more detections. Hundreds, then thousands. And always, with each new planet, the boundaries of the possible widened. But it started here, with a pulsar, with a timing anomaly, with something that shouldn't have been. The idea that the first confirmed exoplanets orbit a neutron star, one of the most extreme objects in the cosmos, feels like a cosmic joke, or a cosmic message, maybe both, that planets are not precious artifacts. They are the natural consequence of gravity, dust, and time. They are stubborn. They form in chaos. They emerge from wreckage. They find a way. It makes you wonder what else we're missing, what patterns we've dismissed, what strange rhythms we've heard and ignored. If we found the first exoplanet by accident, how many more are hiding in data sets already recorded? How many exist in places we've written off as uninhabitable, uninteresting, or unreachable? And it makes you wonder about life, not just planets, but what might happen on them. If planets can form around pulsars, if they can survive radiation and explosion and begin again, then life too might be more resilient than we imagine, more adaptable, more willing to take root in places we'd never consider. Maybe we've been asking the wrong questions, looking for the wrong signs. The first exoplanet wasn't warm, it wasn't welcoming, it wasn't Earth, but it was real, and that reality cracked open the sky. It told us that our solar system isn't typical, that planets are not exceptions, that the cosmos is full of orbits we cannot yet see, and stories we have not yet heard. It reminded us that the universe is not built for our expectations. It is built for possibility, and possibility, it turns out, is everywhere. When a star dies, it doesn't always go quietly. Some end in collapse, others in fire. A few vanish into blackness so complete that not even light escapes. But not all death means emptiness. Not all endings erase what came before. Around these stellar remains, white dwarfs, neutron stars, pulsars, and black holes, planets still orbit. Some were there before, somehow surviving the violence. Others came after, born from the ashes. These are not warm systems full of light and life. They are hushed, scarred places where gravity remains, even when everything else has changed. Take white dwarfs, for example. These are the remnants of stars like our sun, shrunken into spheres no larger than Earth, but hundreds of thousands of times denser. Their light is faint, their heat fading, but their mass still pulls. For a long time, astronomers thought no planets could orbit so close to something that once burned so fiercely. A red giant, in its death throes, swells so large that it should engulf anything nearby. And yet, there are planets, real planets, circling these stellar corpses. Some orbit at astonishingly close distances, their years lasting mere hours. They whip around their dim hosts like whispers of memory, tucked into gravitational pockets that shouldn't exist. In one such system, WD 1856 plus 534, a gas giant the size of Jupiter orbits a white dwarf every 34 hours. The planet is larger than its star. It circles so tightly, it should have been destroyed during the red giant phase, but it wasn't. Maybe it migrated inward after the explosion. Maybe it was already there and survived by a thread. We don't know, but it's there, and that's enough. Its presence tells a quiet story, that even when a star dies, its planets don't always leave. Some stay, some adapt, some hold on. Other systems are stranger still. Neutron stars, born from the cores of massive stars that exploded in supernovae, are some of the most extreme objects in the universe. A teaspoon of neutron star material would weigh 1 billion tons. They spin rapidly, beam radiation, and warp space with their density. And yet, they too have planets. The first exoplanets ever discovered were found orbiting a neutron star, a pulsar, no less, blasting radiation into space while 3 small planets danced around it in precise formation. It was a system built from destruction. The star had already died. The light was gone. But something remained, something reborn. What kind of planet lives in a place like that? Not the kind with oceans and seasons, not the kind with weather or day and night. These are likely cold worlds, stripped bare by radiation. Worlds with no atmospheres, no clouds, just rock and silence. And yet, their motion continues, unbothered, undisturbed, like the slow turning of gears in a forgotten clock. They orbit because gravity doesn't stop, because space doesn't grieve, because once a planet finds its path, it will follow it, even if the star at its center no longer shines. Sometimes we find debris, rings of dust and metal encircling a white dwarf, like the remnants of shattered worlds. These rings are not just poetic. They are the literal leftovers of planetary systems. Moons broken apart, asteroids crushed, planets torn down to their cores. The white dwarf's gravity is immense, and anything that strays too close can be ripped into pieces, ground into a halo of dust. But not all of it falls. Some of it lingers, some of it orbits. These dusty rings glow faintly in infrared, telling us of ancient systems undone by time and tide. In some cases, we even find signs of chemical contamination in the white dwarf's atmosphere. Elements like calcium, iron, magnesium, heavy elements that shouldn't be there because they sink quickly in the star's dense layers. Their presence means something recent has fallen in. A planet, an asteroid, a fragment of something larger. These ghostly fingerprints are the only clues we have to what once existed around these stars. A quiet kind of archaeology, done in light. And then there are black holes, the ultimate end. Not every black hole has planets, at least none confirmed yet. But theoretically, they could. If a planet had the right velocity, the right distance, the right luck, it could orbit a black hole, just like it would a star. It wouldn't be warm. There would be no light, except the distant glow of the accretion disk, if one exists. But it would be stable, a slow orbit around a silence that can't be seen. We don't know what those planets would be like. We've never found one, but there's no reason they can't be there. These are not the systems we imagined when we first thought of other worlds. We pictured sunlight, we pictured warmth, we pictured life. But what we found were echoes, remnants, worlds that linger long after their stars have died. These planets are not hospitable, but they are resilient. They endure where nothing else does. And maybe that tells us something important. That planets are more than just decorations around stars. They are survivors, shaped by fire, by collapse, by unimaginable forces. And still they hold together. Still they orbit. Still they turn, even in the dark. Some might think these systems are tragic, lonely rocks circling dead suns. But there's something beautiful in that loneliness, a kind of perseverance, a memory, the idea that even after a star explodes, its gravity can still sculpt motion, that even in ruin, there is rhythm. And maybe, just maybe, not all of them are silent. A planet orbiting a white dwarf might have a moon. That moon might create tidal friction, heating the planet from within. Or maybe a thin atmosphere clings to its surface, creating just enough pressure for chemistry to begin again. We don't know yet, but possibility lingers, like heat in cooling stone. The universe doesn't end things cleanly. It allows for drift, for remnants, for unfinished stories. A planet orbiting a dead star is one such story. Not erased, not forgotten, just quieter, dimmer, still turning. They weren't supposed to be there. When astronomers first began to find exoplanets around normal stars, they expected the discoveries to mirror what they already knew. Worlds arranged in neat hierarchies, small rocky planets close to the sun, larger gas giants far out in colder regions. That was the solar system's pattern, and for a time, it felt like a law. But the universe has never been much for laws. The first planet found around a sun-like star, 51 Pegasi b, broke every rule. It was huge, half the mass of Jupiter, but it orbited blisteringly close to its star, so close that its year lasted just 4 Earth days. 4. A gas giant where Mercury would be, a world the size of our largest planet, tucked into a space where heat should shred it apart. It was called a hot Jupiter, and it shouldn't have existed, but it did, and it wasn't alone. As new detections rolled in, astronomers found more of these monstrous worlds, massive gas spheres orbiting so close to their stars that their atmospheres boiled, their clouds melted, their skies rippled with chemical chaos. Some are tidally locked, with one face forever scorched in daylight and the other cast in eternal night. On the day side, temperatures soar high enough to vaporize metal. On the night side, those same metals may condense into clouds and rain down as molten droplets. These are not calm planets. They are turbulent, swollen, wind-raked orbs spiraling through furnace-like orbits, and yet they are stable. They endure. It was a problem. Not because they were rare, but because they were common. Too common. So many of the first planets we found were hot Jupiters, simply because they were easiest to detect. Their size and speed caused big, obvious shifts in their star's light. But with each new one came the same question: how did it get there? No model of planet formation predicted this. Gas giants are supposed to form far from their stars, beyond what's called the frost line, where temperatures are cold enough for volatile compounds to condense and build up massive planetary cores. The physics made sense out there. Hydrogen and helium could cling together, snowballing into enormous spheres. But not here. Not near the star. Not in the Inferno. So the theory bent. Maybe hot Jupiters didn't form where we found them. Maybe they formed far out, like Jupiter did, and then something pushed them inward. A slow, spiraling migration through the disk of gas and dust that surrounded their young stars. A gravitational slip, or a nudge from another planet, or the invisible tug of the disk itself. That explanation helped, but it raised new puzzles. How could a planet survive such a journey without falling into the star? Why didn't the heat and radiation strip its atmosphere? Why didn't the friction slow it to destruction? And why didn't we see more planets between the hot Jupiters and their stars, wreckage from the ones that didn't make it? Some scientists proposed that many hot Jupiters are alone because their migration cleared out everything else. As they moved inward, their gravity destabilized smaller planets, flung them into space, or pulled them into chaotic orbits that ended in collision or consumption, a kind of planetary purge. Others suggested different migration paths, violent interactions between planets that caused one to fall inward and another to be thrown away, like a slingshot reversing direction. Still others speculated that some hot Jupiters formed in place after all, under extreme and unlikely conditions, birthed in the heat. There's still no single answer, no unified theory that explains them all, but they are there, close in, fast, impossibly hot, and some are stranger still. Some of these planets are bloated, larger in size than Jupiter but with less mass, as if puffed up by the relentless radiation of their stars. Their atmospheres stretch and swell, sometimes trailing behind them in long, comet-like tails. Some lose mass over time, slowly boiling away into space. Others have winds that scream across their equators at thousands of kilometers per hour, shifting heat from the star-facing side to the night side in uneven, volatile tides. We've even found hot Jupiters that orbit their stars backward against the spin of the star itself. This retrograde motion defies the expectation that planets should coalesce and revolve in the same direction as the star's rotation, born from the same spinning disk of gas. But these planets seem to have broken from their birth conditions. Something tilted them. Something flipped them. Their orbits are not just hot. They're rebellious. They challenge our sense of order. They break the tidy diagrams we teach in schools. They suggest that our solar system is not the template, but an exception. That chaos is not just possible, but common. That planetary systems may be born in violence, shaped by migration and destruction, and still find a kind of equilibrium, still settle into orbits, still endure, even close to the flame. And yet, despite the heat, despite the pressure and radiation, these planets remain in motion. They circle their stars again and again, each year a few days long, each orbit a defiance of expectation. Their skies are not blue. Their clouds are not white. Some may have atmospheres tinged with titanium oxide, others with vanadium, or silicates, or hydrogen ions torn apart by ultraviolet light. The chemistry is fierce, exotic, alien, but consistent. One might expect such planets to be fleeting, to burn out quickly, but they don't. Many are old. Some are billions of years into their short, tight years. That longevity is perhaps the strangest thing of all. It implies that they're not mistakes, not short-lived anomalies. They are part of the cosmic script. They are not meant to exist, and yet they do. What else might exist, then, in contradiction to our models? What other worlds are out there that we've declared impossible, only to find them quietly spinning in the dark? Hot Jupiters were the first major shock, the first real sign that exoplanet science would be about surprise as much as discovery. They are reminders that the universe is not obligated to match our diagrams. It is older than our theories, wilder than our expectations. And so these burning giants continue their orbits, roaring with heat, massive and strange, circling their stars like flames caught in loops. They are not where they should be, but they are where they are. And they are not alone. There are planets that do not orbit stars. No warmth guides their seasons. No sun marks their days. They drift alone through the deep black of interstellar space, lightless and unbound, like stones dropped into an endless ocean. These are the rogue planets. Planets without a home, without a sun, without a dawn. They do not glow. They do not shine. They are hidden from us, moving in silence through the cold, not because they are rare, but because they are dark. And they are many, possibly more than stars. Some estimates suggest that for every star in our galaxy, there could be 2, 5, even 10 rogue planets. 1 trillion or more scattered across the Milky Way, drifting like forgotten seeds on a cosmic wind. We didn't expect them. For a long time, we didn't even look for them. Planets, we assumed, needed stars, needed light, gravity, heat. But the universe is rarely that orderly. Some of these planets were likely born the usual way, within the swirling disks of gas and dust that encircle young stars. They formed from collisions and accretions, just like Earth and Jupiter did. But then, something happened. A gravitational nudge, a close encounter with another planet, a shift in the early dance of orbits that turned chaotic. And one of them, smaller, lighter, unlucky, was cast out, ejected, slung out of its solar system at escape velocity, flung into the black. It didn't burn. It didn't explode. It simply left. Others may have formed alone from the start. In the densest corners of gas clouds, far from stars, a heavy clump might collapse under its own gravity, too small to ignite into a sun, but large enough to become a planet in its own right. These are planetary mass objects born starless, not castaways but natives of the void. Born in darkness, they remain in darkness. Their birth and journey contain no light at all. We don't see them directly, but we catch glimpses. A brief gravitational lensing event, when the planet passes in front of a distant star and bends its light just slightly. A flicker, a shadow, a curve in the path of photons. It's enough to suggest something is there. Massive, cold, invisible by every ordinary means. What are these worlds like? Adrift between the stars. Cold, yes, but not frozen solid. Not always. Some of them may still hold heat from their formation. Radioactive decay or residual compression. A lingering thermal whisper in their cores. If they are large enough, that internal warmth might last for billions of years. Some could have atmospheres thick enough to trap that heat, to cradle it. Some might even have subsurface oceans, warmed from within. Imagine that. A planet in utter darkness, no sun above, and yet, deep below its icy crust, a sea, liquid, moving, waiting. Could life begin in a place like that? Could it survive? We don't know. But the possibility reshapes the question of habitability. We used to think life needed sunlight, needed photosynthesis, needed warmth from a central star. But then we found ecosystems on Earth at the bottom of the ocean, around hydrothermal vents, thriving in total darkness. Entire communities of organisms that feed on chemical energy, not light. If it can happen here, why not there? Why not on a rogue planet, deep beneath ice, in the still warmth of a hidden ocean? And what might drift with them? A moon, perhaps, pulled into orbit during formation, a captured fragment of another system. Or maybe nothing at all. Just a solitary planet turning slowly in an abyss so vast it might never come near another star again. The nearest object to a rogue planet might be a light year away. The nearest sunrise, unreachable. There is something haunting about them, something lonely. We think of planets as part of systems, parts of families, but these are not. These are the wanderers, the orphans, not broken, but unclaimed. And maybe that's why they hold our imagination, because they are the ultimate outsiders, unseen, unknown, yet surely out there in unimaginable numbers, slipping quietly through the dark between suns. A rogue planet might pass through a distant system one day. For a brief time, it could arc through the outer edges of someone else's sky, stirring comets or perturbing orbits before vanishing again into the deep. A visitor no one sees. A gravity ghost. Or maybe, just maybe, it could be caught. A passing star's pull might slow it, claim it, fold it into a new orbit, and suddenly, that rogue is rogue no longer. It becomes a planet again, part of a system, with a sunrise and seasons for the first time in eons. If life had ever begun there, slow, bacterial, waiting, it might suddenly wake, warmed by the light of a sun it had never known. Evolution paused for 1 billion years, resuming with the first glow of a dawn that was never meant to rise. But most will never be caught. They will continue, unlit, unmarked, drifting through the galaxy like memories no one remembers. Their paths curve around nothing. Their skies never change. Just blackness. Just stars, far away, like cold fires. And still, they endure. Just as well as the planets that bask in sunlight. Just as real. Just as old. A rogue planet doesn't need a star to exist. It needs only mass and time and the quiet persistence of motion. And that is enough. Perhaps there's something to admire in that. The resilience, the independence, to move without orbit, to journey without a center. They are not failed planets. They are not lost. They are simply alone. And in that aloneness, they carry a truth the stars can't hold. That not all light comes from fire. That not all warmth comes from proximity. That not all life, if it exists, needs to be seen to be real. They are drifting still. Countless worlds in the dark, unseen and unnamed. Some the size of Earth, some larger than Jupiter, some frozen, some still warm. Moving not towards something, but simply through, always through. Somewhere far from here, under a pale and dying star, there is a world where the rain is not water, not snow, not ice, but metal, liquid iron, falling from a sky the color of rusted steel. Droplets heavier than bullets, heated to thousands of degrees, pouring sideways through the air like molten sleet. Not drifting gently, but driven sideways by winds so fast they could rip continents from the ground. 8,000 kilometers per hour, the speed of a supersonic scream. This is not science fiction. This is not fantasy. This is weather. Real weather. on real planets, orbiting distant suns. WASP-76b is one of these. A gas giant tidally locked to its star, always showing the same face to the light. That day side is blinding and brutal, heated to more than 2,400 degrees Celsius, hot enough to vaporize metals into gas, iron, magnesium, silicates, elements that would be rock on Earth, turn into atmosphere. On the night side, it's cooler, though cool is a relative term. Still over 1,000 degrees, but enough to let some of that metal vapor condense. And so, the planet breathes. Gas rises, whips around to the dark side, and rains. Rains metal, not water, not snow, but a metallic monsoon falling from a black sky. Imagine what that would look like. A horizon blurred by glowing vapor. Clouds made of atoms we associate with swords and skyscrapers. Droplets falling in silence, too heavy for storms, too hot for life. No forests, no oceans, just endless atmosphere, dense and deep, lit by the amber pulse of its sun. Lightning, if it exists, would crack through clouds of iron and titanium oxide, illuminating landscapes we'll never walk on. If there is a surface, it's hidden below layers of pressure and gas, unreachable even by imagination. But the sky is real. The rain is real. WASP-76b is only one of many. There are other hot giants, other planets with skies that bend our definitions of weather. On HD 189733b, another gas giant, the winds blow shards of silicate, glass, at thousands of kilometers per hour. It rains glass sideways, not in little panes or flakes, but as fine particles sharp enough to cut through steel. The planet is deep blue, not from water or reflection, but from the scattering of light through its silicate atmosphere. It looks peaceful from a distance, like a calm ocean in space. But that calm is a lie. The blue is a storm. These storms do not follow patterns we know. There are no seasons here, no jet streams or trade winds. These are worlds locked in eternal extremes. On tidally locked planets, one side is always lit, always burning, the other always shadowed and strange. The heat gradient alone drives winds at impossible speeds, transferring energy in chaotic loops, carving the atmosphere like water cutting stone. And in that carving, chemistry happens, exotic, violent, surreal. Some exoplanets have clouds made of rubies and sapphires, aluminum oxide suspended in heat and wind. Others might host ammonia snowstorms, hydrocarbon fogs, methane flares. On some, sulfur might rise and crystallize, turning the air into a golden haze. Still others may not have weather at all, just a heavy silence, a gravity too strong for anything to rise. But where weather does exist, it is shaped by physics we understand, yet expressed in ways we never expected. Gravity, heat, pressure, rotation, the same ingredients with different recipes. We've only begun to model these atmospheres. We don't have photographs. We don't have probes drifting through alien clouds. What we have are spectral fingerprints, traces of light bent through layers of gas, dimmed and warped by motion and molecules. From that light, we infer temperature, composition, wind, rain. It's a kind of astronomy that borders on poetry. We read the songs of Starlight to learn the shape of distant storms. Even on planets more like Earth, the weather would be strange. A slightly thicker atmosphere, a different mix of gases, a stronger tilt. Any of these could lead to climates beyond our experience. Constant lightning, permanent twilight, rains that never stop, suns that never set. We don't know what is typical. We only know what is possible. And what's possible seems to stretch wider every year. We once thought Earth's weather was complex, and it is. But it is a softness, a narrow band of survivable balance. Elsewhere, nature is less gentle. It boils, it hurls, It tears. But even there, it follows rules. Thermodynamics, chemistry. The equations are familiar. It is the outcomes that are alien. There's something humbling in that. To realize that storms rage on planets we'll never see. That weather, ephemeral, chaotic, vital, is not unique to Earth. It is a feature of the universe, a side effect of heat and motion. And maybe, one day, it will guide us. Because weather leaves traces, rain leaves patterns, clouds change the way light reflects. And with better instruments, we may one day read the atmosphere of a distant world and know, just from its flicker, if water ever fell there, if something once breathed, if something might still. But for now, we imagine, not just water, but iron, not just snow, but glass, not just wind, but walls of air moving faster than sound. We imagine skies we cannot survive, but which still obey the same physics as our own. We imagine, and then we listen to the wobble of starlight, to the spectrum of rain no eye can see. And out there, somewhere, it is raining. Not here, not now, but always, in the dark between stars, on a world whose name we've just learned to pronounce. Droplets of molten metal are falling through clouds of vaporized rock, swept sideways by the breath of a wind that never stops. It was easy to assume we were the rule, that Earth, with its oceans and oxygen and comfortably mild sun, was the prototype, the model, the quiet standard against which all other planets could be measured. For decades, when we imagined life elsewhere, we looked for versions of ourselves, a rocky planet, a stable orbit, liquid water, an atmosphere just thick enough to hold warmth, but not so thick as to choke. Earth-like. That was the phrase, Earth-like, as if Earth were ordinary. But the deeper we look, the more we begin to understand. Earth is not typical. It is strange, remarkably, improbably strange. Start with the orbit. Earth's path around the sun is unusually circular, not perfectly, but close enough that our seasons stay balanced, our temperatures mild, our climate stable enough for complex life to evolve and survive. Many exoplanets we've found follow far more eccentric orbits, long ellipses that swing them dramatically closer or farther from their stars over the course of a single year. Those worlds would face wild swings in temperature, sudden seasons, years that pulse with extremes. And yet here, Earth glides in its gentle loop, quietly predictable. Then there's the tilt. Earth leans just a little, about 23.5 degrees, which gives us seasons, but not too much. Just enough to stir the air, shift the sun, move the rains and snows in time with life. Some planets have no tilt at all, locked in endless equinox, frozen in monotony. Others tilt too far, flipping between deep freeze and searing heat. Ours spins at the perfect angle to keep things in motion, but not in chaos. And that spin is another anomaly. Earth rotates once every 24 hours, fast enough to spread heat around, slow enough not to fling itself apart. But many exoplanets, especially those close to their stars, are tidally locked. One side always faces the sun, bathed in endless day, while the other lies in permanent night. Those worlds are divided into hemispheres of fire and ice, with a twilight ring of possibility in between. Earth, by contrast, rolls gently through light and dark, a rhythm we take for granted. And then there is the moon. Our moon is huge, far larger, relative to our planet, than any other in the solar system. It stabilizes Earth's tilt, keeps our seasons from wandering, and stirs the tides in a way that may have once nurtured life in the shallows. The leading theory is that it was born from violence, a colossal impact with a Mars-sized body early in Earth's history, flinging molten debris into orbit that coalesced into our luminous companion. A freak event, a cosmic accident, and yet without it, we might not be here. The Earth's crust is broken into plates, tectonic plates that drift and grind and dive beneath one another, recycling the planet's surface over eons. That movement helps regulate carbon, balances the climate, and shapes the continents. We don't yet know how common plate tectonics are, but so far, Earth is the only place we've seen them. Another rare feature, another mechanism that helps keep the planet alive. Even our water is unusual. We have vast oceans, yes, but not too much. Some planets may be ocean worlds, entirely covered in water, with no land at all. Others are dry, barren, with nothing to evaporate, nothing to rain. Earth struck a balance. Water to carve rivers and clouds, land to build mountains and forests. Not too wet, not too dry, just enough. And then there's the atmosphere, a fragile veil of gases, thin as the skin on a soap bubble when viewed from space. Mostly nitrogen, with enough oxygen to breathe, enough carbon dioxide to warm. But not too much. Venus has an atmosphere too. Thick, choking, crushing. Its clouds trap heat until the surface glows red, hot enough to melt lead. Mars has the opposite problem. Too thin, too cold, too quiet. Earth, somehow, found a middle ground. That middle ground might not be common. And what about life? On Earth, life has been here for billions of years, but complex life is new. Intelligence, consciousness, language. All of it has happened in a sliver of time so narrow, it's almost invisible on the scale of the planet's history. If Earth had blinked, if the climate had shifted, if the orbit had wobbled, we might never have emerged. And if life did begin elsewhere, would it evolve into something like us? Would it think, build, wonder? Or would it remain as microbes, unseen and silent, hidden in oceans or under ice? We don't know. But what we do know is this. Earth is not the standard. It is not the rule. It is weird. Weird in its size. Not too small to lose its atmosphere. Not too large to crush everything in pressure. Weird in its composition. Iron core, rocky mantle, liquid water. Weird in its history. Born in fire, cooled into green. The more planets we find, the more it becomes clear that Earth is a statistical outlier, a rare coin flipped just the right way, multiple times in a row. And yet, here we are. It's tempting to think of ourselves as the center, the baseline. But maybe we're not. Maybe we are the edge case, the beautiful exception, the one improbable combination among trillions of worlds that holds oceans and mountains and cities and dreams. That doesn't mean life isn't out there, but it might mean we need to look in stranger places, planets with thicker air, worlds with different chemistries, moons orbiting giants, shadows circling dim suns. Life may be common, but life like us, on a world like this, might be something else entirely. A miracle not of magic, but of math. A convergence of chance and time and dust. So we look outward, and we remember. The Earth is not a template. It is a story, one of many, a rare one. And that rarity is not a burden. It is a wonder, a reason to pay attention, a reason to protect what we have. Because in all the darkness, among all the stars, we may find thousands of planets, millions, but we will not find another Earth. Not exactly, not quite. Only this one. For now, far from here, orbiting a faint and flickering star, there may be a planet so dense, so carbon-rich, so relentlessly compressed, that its very crust is made of diamond. Not scattered like gems in a riverbed, or embedded in rock like buried treasure, but stretching for hundreds, perhaps thousands of miles. An entire world forged under pressure so immense it sculpted its surface into crystal. Hard, shining, alien. We didn't expect this. Not at first. Diamonds, on Earth, are rare. Fragments formed deep underground, where heat and pressure twist carbon into symmetry. They rise slowly, carried upward by violent events, arriving in veins and pockets like secrets. We think of them as luxury, as symbols of permanence and strength. But in space, in certain places, diamond may be not rare at all. It may be the bedrock. Take 55 Cancri E. It orbits so close to its star that a year lasts only 18 hours. A world scorched by heat, but with a mass nearly twice that of Earth and 8 times the pressure. Its parent star is carbon-rich, and if the planet formed from that same material, then it too could be saturated with carbon. Compressed, rearranged, transformed. Surface rocks that would shimmer, mountains that would glitter. A planet that is, quite literally, shining in the dark. But it wouldn't look like a jewelry store, not the way we imagine. This isn't cut glass on velvet or stone set in gold. It would be raw, rough. A landscape of crystal plains and jagged ridges, glinting with hard light beneath a white-hot sun. There may be no oceans, no clouds. The atmosphere, if it exists at all, could be thin and choked with vaporized metals. It might not rain, but if it did, it would be carbon soot, falling on a ground already turned to stone. And beneath that surface, more diamond, layered, growing denser with depth, turning eventually to graphite and then, deeper still, to metallic carbon in exotic forms. A glittering geology we can only imagine. Beneath the crust, beneath the molten mantle, the core itself might be diamond, compressed by its own gravity into something sharp, enormous, and eternally hard. This is not just a trick of materials. It is a story of chemistry and environment, of what happens when the right elements meet the right pressures for long enough. Our solar system gave us silicates and iron, a world of dust and rust and green. But in other places, under other suns, carbon is king. There, planets may form from graphite like clay, then harden into gemstone, not because they are special, but because the ingredients said so. And it doesn't end there. If planets can be made of diamond, what else can they be? We've found planets with molten glass skies, with clouds of silicate, with atmospheres laced with sodium and vanadium. We've seen hints of carbon monoxide winds, of methane seas, of sulfuric snow. Nature doesn't follow our aesthetics. It doesn't care what feels right. It builds what it can from what it has. In a carbon-rich system, diamonds are not rare. They're inevitable. But rarity is not the point. What matters is what these diamond worlds represent. A shift in how we see planets, how we define what a world even is. Earth is solid and wet, with tectonics and weather and life. But remove one variable, like the oxygen content, or the star's metallicity, and you might get something entirely new. Not broken, not failed, just different. A diamond planet is no less a world. It just glows in other ways. Could anything live there? That's harder to say. The temperatures on known diamond candidates are high enough to melt metal, hot enough to sterilize almost anything we'd recognize. But life, if it exists, would not need to be like us. It may not need water or oxygen or coolness. It may not walk on legs. It may not even think, but it might feel. It might move. It might evolve in the quiet furnace of a gem-colored world where sunlight burns white and the land itself cannot be scratched. Or perhaps not. Perhaps these planets are lifeless, still and shining, waiting for no one. Even so, they pull at the mind. Because we know diamonds, in our way, we carry them on fingers, we carve with them, we press them into drills and set them into crowns. They are among the hardest materials we know, timeless, enduring, and now, perhaps, not only the stuff of Earth's deep mantle, but the crust of entire alien worlds. Planets that never broke apart, planets that never cooled like ours did, planets that were compressed and stayed that way, locked forever in the beauty of pressure. And if you stood on one, if you could survive the heat and gravity and radiation, what would you see? Would the horizon gleam? Would the ground crunch beneath your feet like glass, or echo like crystal under weight? Would you see your reflection, faint and warping, in the angled planes of the stone below? Or would it be dark? Not black, but sharp. Cold, not in temperature, but in presence. A world without weather, without time. A landscape formed not through erosion or uplift, but through sheer weight and silence. We may never know, but we can imagine. We can follow the numbers, the spectral lines, the trembling pulses of starlight, and read the clues. And when we do, we find that the universe is not only stranger than we supposed, but stranger than we ever dreamed. There are worlds of metal, worlds of vapor, worlds of fire, and yes, there are worlds of diamond, not imagined, not metaphorical, but real, turning slowly in the dark, catching light in hard reflections, waiting in silence, not to be discovered, not to be owned, but to exist. That, in itself, is enough. There is a type of planet that doesn't exist here, not in our solar system, not among the 8 names we memorized in school. It sits in the gap between Earth and Neptune, larger than a rocky world, smaller than a gas giant, something in between. We call them super-Earths, though the name says more about us than it does about them. Bigger than Earth, but not by much. Not enormous, just more. And they are everywhere. More than half of the exoplanets we've found fall into this category. They come in all flavors, some scorched and dry, some cloaked in thick atmospheres, some possibly hiding oceans miles deep. They're not rare. They're the opposite of rare. They are the cosmic norm. And yet here, in our own star system, they are completely absent. We are the exception, the oddity. Our planetary lineup skips this size class entirely, like a missing rung in a cosmic ladder. It wasn't always obvious. For a long time, our understanding of planetary types was shaped by what we could see. Mercury, Venus, Earth, Mars, small and rocky. Then the giants, Jupiter, Saturn, Uranus, Neptune, gas and ice, swirling with storms and rings and moons. No planets in between. So we assumed that was standard, that the universe followed our blueprint. It doesn't. What we've discovered instead is that the most common kind of planet is one we'd never seen before. The in-betweeners, the almost Earths, the nearly Neptunes, super-Earths. Some of them are only slightly larger than Earth, maybe 30% more in diameter, a bit heavier, with more gravity tugging at your feet. Others are massive. 10 times Earth's mass, thick with atmosphere, likely too hot or too crushed for life as we know it. But many fall into a promising range, not too big, not too small, not too dense, not too light. Enough mass to hold an atmosphere, enough surface area to host oceans, enough gravity to hold on to water, and maybe life. And they're everywhere we look. Kepler 22b, HD 40,000. 307 grams, Gliese 581d, Tau Ceti, F. These are names, cold and coded, assigned by catalog. But behind each one is a world. A real place, circling a real star, tracing paths through gravity and light. Some are close, cosmically speaking, just a few dozen light years away. Close enough that photons reflecting from their stars are already whispering into our instruments. Some might even be visible with the right eyes, the right telescope, the right angle of silence. We don't know what they look like. Not yet. But we have hints. A super-Earth could have a rocky surface, with mountains taller than Everest and valleys deeper than any trench on Earth. It could have volcanoes powered by internal heat, erupting not with lava, but with ammonia or methane, painting the sky with strange storms. It might have a dense atmosphere, thick with clouds and lightning, or it might be wrapped in haze, muting the sun, casting everything in orange light. It could have oceans, vast, deep, boundless, not shallow seas like ours, but water stretching hundreds of kilometers down, pressing against the crust with unimaginable force. Or it might be ice, locked in a slow rotation, reflecting its star like a distant moon. Some super-Earths orbit in their stars' habitable zones. The Goldilocks belt, not too hot, not too cold, where water could stay liquid, not guaranteed, but possible. And where there's water, there could be life. We don't know what form that life would take. We barely know what to look for. But the ingredients are there. The conditions are plausible. And the numbers, the numbers are staggering. Hundreds of billions of stars, most with planets, many with super-Earths. Even if just a tiny fraction are in the right zone, with the right chemistry, the right calm, the potential multiplies beyond imagination. These planets may not be rare at all. What's rare is us. Because in our solar system, we have the small rocky worlds, and then we jump straight to gas giants. No middle ground, no super-Earths, and no clear reason why. It may be a fluke of formation, a timing issue. Perhaps the gas giants formed early and swept the region clean. Perhaps a super-Earth once existed and was thrown into the sun, or ejected into the dark. Or perhaps our solar system is just one of many kinds. Neither better nor worse, just different. It's a strange feeling, realizing that the most common type of planet isn't one we've ever seen up close. We can model them, infer their densities, map their orbits, guess at their climates. But we can't touch them. Not yet. They exist as suggestions, as signals, as dips in starlight and curves in data. But they are out there. They turn beneath alien suns, wrapped in storms and silence. They endure the pull of gravity, the lash of radiation, the sculpting of time. Some have been there for billions of years, older than Earth, older than our sun, waiting without purpose, just existing, just being. And maybe, one day, we'll go. Not soon, not quickly, but eventually. When our machines grow faster, when our understanding deepens, when we've learned to cross the darkness with more than dreams, and when we do, the first worlds we reach may not be Earth-like. They may be stranger, heavier, newer, but they will be real, and they may welcome us with sights we've never imagined. Until then, we look from afar. We measure their shadows. We watch their stars dim and brighten and dim again, and we wonder, not if they're there, but what they're like. Because super-Earths are not theory. They are not question marks. They are the answer that keeps appearing, again and again, in every corner of the galaxy. They are the rule, and we are the exception. Imagine standing on the edge of a sea that isn't made of water. It doesn't shimmer with reflections of the sky or lap gently at a sandy shore. Instead, it glows, a molten orange red, pulsing like breath, stretching into the distance like a living thing. This is not a sunset. This is the surface, a world where rock flows like water and the air is heavy with vaporized minerals. This is a lava ocean, and on some exoplanets, it's not the exception. It's the norm. We call them lava worlds, but names feel small here. They're officially classified as ultra-short-period planets, bodies that orbit their stars so closely that a year lasts only a day or two. They're pulled into a state called tidal locking, where one side always faces the star while the other remains in endless night. On the day side, temperatures soar past 2,000 degrees Celsius, hot enough to melt iron, silicate, even the surface itself. Rock becomes liquid, mountains crumble into fire, whole continents dissolve into magma. Take Coro T7b. It orbits its star in just 20 hours. On its day side, the heat is intense enough to vaporize stone, to strip atoms from the surface and launch them into the thin atmosphere. There are no forests here, no clouds, no water. Just boiling rock and skies filled with metal vapor, glowing faintly in hues we have no words for. If you were to set foot on it, if somehow you could, it wouldn't be like standing on a solid world. It would be like balancing on a simmering pot, the ground shifting, hissing, steaming underfoot. But move to the night side, and everything changes. Over the limb of the planet, the magma hardens, the glow dims. The air, if any remains, grows still. Here, it might be cold enough to freeze gas, to let rock solidify into sharp, glassy crust. There may be frost made not of water or carbon dioxide, but of silicates or iron. It would be a landscape of frozen shadows and razor-thin silence. No wind, no heat. Only the distant pressure of a star just over the horizon, pulling, always pulling. In between these two extremes, between fire and ice, there may be a twilight band, a place of relentless storm, winds howling from hot to cold at speeds unimaginable, dragging vaporized rock across the sky, forming clouds of silicate that crystallize and fall like glittering rain. Not water, not snow, but shards of minerals falling sideways at thousands of kilometers per hour, slicing through air that itself is half molten. It is a world built from opposites, violence and stillness, flame and stone. And these are not isolated examples. There are others. Kepler 10b, K 2141, b, TOI 849b. Each one slightly different, shaped by its own star, its own mass, its own chemistry. Some may have oceans 100 kilometers deep, not of water, but of liquid rock, endlessly churning, fed by rivers of lava pouring from cliff-sized vents. Others may have a crust only a few feet thick, floating precariously atop a planetary sea of magma. Beneath that surface, convection currents, massive and slow, dragging molten rock in loops that last centuries. On some of these worlds, it may rain rock. Not metaphorically, not poetically, literally. Vaporized silicates rise into the sky, cool, condense, and fall again as droplets of stone. The same way rain cycles on Earth, but with entirely different materials. These are geologies we do not yet understand. Climates shaped not by water and sunlight, but by elemental fury. Weather that burns. What would a sunset look like here? If you stood in that twilight band, if you turned your eyes toward the horizon, what would you see? Would the sky shimmer with red and gold, or burn white with intensity? Would the clouds glow from within, like lanterns of smoke and metal? Would lightning flash silently between layers of vaporized rock, or would there be no sound at all, just the roar of heat itself? We've never seen one of these skies. Not directly, but we've measured their effects, the tiny shifts in starlight, spectral fingerprints of metals and minerals, thermal maps that glow in infrared. From these, we piece together stories. We imagine the light, the heat, the tides of stone. We wonder how such planets form, and more curiously, how they survive. Because by all logic, these worlds should be torn apart. Their orbits are so tight, so close to their stars, that the gravitational forces involved are immense. Tidal stresses can rip a planet from within, cracking its mantle, liquefying its crust. And yet these planets remain. They orbit and endure. Not because they're protected, but because they're hardened, scarred, boiled, tempered by their own suffering. It's tempting to see them as infernal, as places of torment, but the universe isn't cruel. It's just vast. And these planets are simply what happens when gravity and matter and time collide in particular ways. They are not mistakes. They are not cursed. They are just extreme. And maybe that's the most unsettling part. Because once, we thought we understood what a planet was. A sphere of rock or gas, orbiting a star. Maybe with an atmosphere. Maybe with life. Something like Earth. Something like Jupiter. But lava worlds rewrite that idea. They show us that planets can be oceans of fire, that geology can be fluid, that a surface doesn't have to be still, that weather can melt, and still they turn. They orbit in silence, blistering and bright, carving their paths through starlight. They do not ask to be known. They do not need to be understood. They are not waiting for visitors. They simply exist, flickering like sparks in the dark. And from here, across the light years, we can only watch, measure, wonder. These are places no spacecraft has visited, no eye has seen, no probe has touched. Yet they are real as mountains, as real as rain, as real as the heat you feel when you close your eyes and imagine standing on the edge of a sea of lava beneath a sky that glows not with sun, but with fire. Somewhere out there, those oceans still boil, those storms still howl, those shadows still freeze. A planet moves through fire, and it does not break. It shines. There's a phrase you hear often in astronomy, polished and repeated like a lullaby, the habitable zone. It sounds so simple, so reassuring. A ring of distance around a star where a planet, if it exists, could be not too hot, not too cold, just right. The Goldilocks zone. A place where liquid water might pool on the surface, where life could, in theory, take root. It's a neat idea, easy to grasp, but the truth, like most things in the universe, is far less tidy. Because habitability isn't a line on a graph. It's not a boundary you cross and suddenly everything is teeming with life. It's messier, stranger, deeper, and in some cases, much darker. The idea came from Earth. Our distance from the sun, our orbit, our temperature, it all seemed perfect. So we cast that perfection outward, looking for similar conditions around other stars. But what we've come to learn, slowly and humbly, is that Earth's habitability is as much about what happens below the surface as it is about how much sunlight we get. Atmosphere, magnetic field, geological activity, water retention, timing, luck, even catastrophe. Some planets may sit squarely in the habitable zone and still be utterly dead, choked in carbon dioxide, stripped of atmosphere, dry as bone. Others may lie well outside that zone and still carry the quiet heartbeat of warmth beneath their surface. These are the ones that force us to rewrite our definitions, the ones that remind us how little we truly know about where life might bloom. Take Europa, a moon of Jupiter, far from the sun, encased in ice. It's nowhere near the traditional habitable zone, no sunlight strong enough to melt the surface. And yet, beneath that crust, there may be an ocean, a liquid, vast, stretching for hundreds of kilometers, kept warm not by the sun, but by the moon's own twisting, squeezing motion as it orbits Jupiter, tidal heating, friction turned to warmth, an engine powered by motion instead of light, or Enceladus, smaller still, but throwing plumes of salty water into space, jets that rise through cracks in the ice, fed by pressure and heat from within, a cryovolcanic breath. If life exists in these oceans, it would never see a star. It would never feel sunlight. It would live in the deep, by chemical gradients and hydrothermal vents, feeding not on photosynthesis, but on something more primitive, and maybe more common. Now imagine a planet like that, not orbiting a gas giant, but free-floating, a rogue planet. Cast out of its system, lost between stars, drifting through blackness colder than anything we can fathom. No starlight, no warmth from above. But if it's large enough, with a thick, insulating atmosphere and an active core, it could still harbor warmth. Beneath layers of rock and gas, geothermal heat could maintain an ocean. Entire biospheres hidden in the dark, traveling the galaxy in silence, lit only from within. It's not just science fiction. It's thermodynamics. It's chemistry. It's the universe telling us life might not need what we thought it needed. Even on planets that do orbit in the habitable zone, the picture is complicated. Some may have runaway greenhouse effects, atmospheres thick with carbon dioxide or methane, trapping heat until oceans boil away. Others might be locked in global ice ages, reflecting sunlight back into space, never warming enough for liquid water to form. Some might rotate so slowly that one side scorches while the other freezes. Others may have such eccentric orbits that their climates swing wildly between extremes. And yet, life is adaptable. On Earth, we find microbes in boiling acid, bacteria under Antarctic glaciers, creatures thriving at the bottom of the ocean, where the pressure would crush a human in seconds. We find persistence in places that should be barren, resilience in the face of everything we call inhospitable. So when we look at other worlds, why would we expect life to be picky? Why would we assume it must mirror ours? Maybe habitability is more about potential than perfection, a range of conditions that allow for possibility, a window that doesn't need to be wide, just open. And there's more. Consider planets with thick atmospheres of hydrogen. These gases can act as insulators, trapping heat from within, creating conditions for liquid water even at great distances from a star. These aren't Earth-like by any measure. They're more like mini Neptunes with dense envelopes, but their interiors could host oceans, even life. If a civilization evolved there, it might never see stars. It might know only the glow of its own atmosphere, the slow churn of pressure and gas. What would that sky look like? What would wonder mean in a world where the stars are hidden? The more we learn, the more the definition of habitable stretches. We once believed Mars was the best candidate for life because it looked like Earth, dry, rocky, in the zone. But now we know there are better candidates, stranger ones. Super-Earths with thick atmospheres, ice moons with hidden seas, rogue planets with geothermal cores. The conditions for life may not be rare. They may be embarrassingly common. And the universe, in its quiet vastness, may be teeming with possibilities we haven't even thought to name yet. So the habitable zone is a beginning, yes. A place to start looking, a compass. But it's not a destination. It's not a promise. It's just one way to ask the question, where could life exist? The real answers live in the margins, in the subsurface oceans, in the atmospheres of gas giants, in the storms of tidally locked worlds, in the dark, in the heat, in the places where no one thought to look. And as we expand our understanding, so too does our sense of wonder. Because if life can find a way in these unlikely corners, then maybe it's not rare. Maybe we're not special. Maybe we're just early. Maybe the universe is already full, and we've only just begun to see where life might be hiding. Somewhere out there, under a sky touched by two dawns, a planet circles in rhythm with a dance more complex than any we've known. Not a lone sun rising each morning, but two, twin stars pulling light across the sky in arcs that shift with time. Sometimes close, sometimes far, sometimes circling each other in a slow embrace, while their planet orbits from afar, quietly watching. This is not science fiction. This is not imagination. These are circumbinary planets, and they are real. For a long time, they were a fantasy, a lovely one, made iconic by the image of a young hero watching twin suns sink into a desert horizon. We thought them unlikely, unstable, even impossible. How could a planet survive the constant tug of war between two stars? Wouldn't the gravity tear it apart or fling it into the dark? For decades, that was the thinking. That binary stars might have planets, yes, but not ones that orbited both, not ones that circled like moons around gods. And yet, now we know better. The first confirmed circumbinary planet was found in 2011, Kepler 1.6b, a cold, Saturn-sized world orbiting a pair of stars that dance around each other every 41 days. The planet itself takes 229 days to complete its path, gently weaving around both suns in a slow, stable loop. It was a revelation, not just for what it meant scientifically, but for what it meant emotionally. The image had come true. Tatooine wasn't just a dream, it was a type, and there are more. Kepler 3, 4b, Kepler 3, 5b, Kepler 4.7. With multiple planets in orbit, each one a testament to how the universe loves complexity, how it permits balance in the most unlikely places, because this isn't a system that should be peaceful. It's one where gravitational forces constantly shift and flex, where light comes from more than one direction, where seasons may not be tied to a single sun, but to the choreography of two. Yet somehow, the planets endure. They find the space between the pulls, the harmony and the chaos. If you stood on one of these worlds, the sky would never be still. The brightness of day would fluctuate, changing with the angles of the suns. Shadows would stretch in strange directions, double and overlap. You might see one sun rise while the other sets, or both rise together, casting the land in a light too wide for comfort. Nights wouldn't always be dark. One star might dip below the horizon, while the other lingers just above it, casting twilight across the land long after it should be night. Time would be slippery. Familiar patterns would bend, but beauty would be constant. There's something inherently poetic about two stars sharing the sky, about a world that survives between them, about balance born not from symmetry, but from motion. These planets aren't static. Their orbits are dynamic, elliptical, responsive. The stars themselves shift, sometimes drawing closer, sometimes apart, and the planet must adjust, must respond. And yet, over thousands, even millions of years, stability persists. These are not flukes. They are systems. Delicate, yes, but resilient. There's a term astronomers use, dynamical stability. It means that a system can last over long timescales without falling apart, that the math checks out, that the paths hold. And it turns out that circumbinary planets, despite everything, can be dynamically stable, even predictable. The stars may move quickly, but the planets orbit farther out, where the tug-of-war is less violent. From that distance, the dual suns blur into a single gravitational partner, a center that can be circled, a home, and it changes what we look for, because binary stars are common, more common than single stars, in fact. If planets can exist around them, then the number of potential planetary systems just doubled, perhaps more. It means that the variety of solar systems out there is broader than we thought. That Earth's simple arrangement, one star, one planet, is not the standard. It's just one configuration of many, a quiet solo in a universe filled with duets. Of course, not all circumbinary planets are like the one in the story. Most of them, so far, are gas giants, too hot or too cold for life, as we know it. But that doesn't mean smaller, rocky worlds don't exist among them. We simply haven't found them yet. The signals are subtle, the methods imperfect, but they are improving. With each new telescope, each new set of eyes turned to the sky, our chances grow. And so does the wonder, because to imagine a world with two suns is to imagine a new kind of life, a new rhythm, a new kind of day. Think of the myths that would form, the calendars, the stories, cultures shaped by twin dawns, twin gods, twin lights, languages with words for skyfire and double sunset, art built in symmetry and shadow. What kind of beings would evolve under such a sky? What kind of dreams would they have? We don't know. We may never know. But the idea alone shifts us. It pulls the boundaries of possibility outward. It reminds us that the rules are not as rigid as they seem, that gravity, when given time, can choreograph astonishing things, that light does not always come from one source, that planets can, and do, thrive in complexity. They orbit, they balance, they last. Somewhere, right now, a world is turning slowly beneath two suns. The sky is lit in ways we cannot imagine. The seasons move with a rhythm we've never felt. And though we are far from it, light years away, its existence folds quietly into ours, proof that the universe is wider than we dreamed, that even the stories we once called fiction might already be written in starlight. And above that distant horizon, the suns rise again, together. In the quiet precision of astrophysics, there are rules, not laws etched in stone, but patterns, probabilities, expectations. things that tend to happen when gas and dust collapse under gravity's gentle insistence. Out of the spinning disk around a young star, planets are born. Small, rocky ones near the heat, gas giants farther out where ices can solidify. It's elegant, predictable, a model that makes sense until the universe reminds us that it doesn't owe us sense at all. Because some planets shouldn't exist, not by the rules we know, not by the models we've trusted. They're outliers, contradictions, worlds that formed too fast, or too close, or too large in regions where there wasn't supposed to be enough material. Planets that punch holes in our understanding simply by existing. Take the hot Jupiters again, but look deeper. Not just the fact that they orbit close, but how close. Some skim the edges of their stars, completing full orbits in less than a day. These aren't warm, they're searing. Their atmospheres blister and puff like steam from boiling water. If they formed in place, the heat would have evaporated their building blocks before they had a chance to become anything. But if they migrated inward later, how did they stop before falling in? What hand held them back from the edge? We don't know. We have theories. Ideas about gravitational interactions, about planets nudging each other into new orbits, like dancers brushing past one another in a crowded hall. But the math doesn't always line up. Some of these planets seem too big to have been pushed so delicately. Others sit alone, with no visible culprit to blame, and still they cling to orbits that should have torn them apart. Then, there are the giants in the wrong neighborhoods. Massive planets discovered in the outer edges of young systems, where the protoplanetary disk should have been too thin to form anything so large. Like building a cathedral out of sand. The material just wasn't supposed to be there, and yet, there they are. Worlds 10, 20 times the mass of Jupiter, drifting far from their stars like kings exiled to the wilderness. They make us wonder if planets can form faster than we thought, or by methods we haven't fully considered. Perhaps from gravitational collapse directly, skipping the slow accretion entirely. Born, not built. And then there are the strange hybrids. Planets so dense they verge on becoming stars, with cores of metallic hydrogen or exotic matter we can't quite simulate. Others, with densities so low they're barely more substantial than air. Super puffed, like cosmic cotton candy, with volumes dozens of times that of Earth, but masses barely heavier. Some of them orbit red dwarfs so closely that they should be stripped bare by flares and radiation. Yet they persist, bloated and defiant, soaking in the heat, like they've found a way to survive through sheer improbability. One planet, named WASP-17b, is twice the size of Jupiter, but only about half its mass. If you dropped it in water, if such a thing could be done, it would float. Another, HD 106906b, orbits its star at a distance over 700 times farther than Earth does from the Sun. That's 20 times farther than Neptune. It takes nearly 15,000 years to complete a single orbit. It shouldn't be there. Nothing in our models explains how it could have formed so far away and stayed gravitationally tethered. And yet, astronomers find these worlds not with telescopes pressed to eyepieces, but through patterns, through dips in starlight, changes in timing, wobbles in motion. Each discovery begins as a whisper, a question in the data, and with enough confirmation, enough rigor, the whisper becomes a voice, a story, and sometimes that story doesn't match the ones we've written. That's where the wonder begins, because every time we find something that shouldn't be there, we're offered a glimpse into the real rules of the universe, not the ones we guessed, but the ones that actually are. It's like realizing the map you followed all your life was only a sketch of one coast, and now you're seeing the outline of an entire continent. You're not wrong. You're just unfinished. There's a strange humility in that. Science, at its core, is not about certainty. It's about being willing to change your mind, to expand the model, to let the universe be bigger than your expectations. And exoplanets, especially the weird ones, demand that we do just that. They tell us that star systems aren't tidy, that planets may grow large in small spaces, or hold together where they should fall apart. That gravity, chemistry, and time are capable of arrangements we haven't imagined. They show us that the universe is not built to please our sense of logic. It is built instead to be what it is, and sometimes what it is impossible. But impossibility, it turns out, is often just unfamiliarity, a sign that we've come upon something new, something with its own set of rules, its own conditions, a hint that our view is still narrow, still human. The planets that defy our models are not mistakes. They're messages, not from anyone, but from the cosmos itself. A reminder that exploration is not just about distance. It's about letting go of what you thought you knew. So we listen, we rewrite, we begin again, and each time we do, the map grows wider, the models grow stranger, the night sky becomes a little more alive, because for every planet we expected, there are others waiting to surprise us. Worlds that shouldn't exist, but do. There are planets where the sky never changes, where the stars never shift, where the sun never sets, and night never lifts. One side of the world burns beneath an eternal noon, the other lies frozen in permanent midnight. These are tidally locked planets, worlds caught in the grip of their stars, rotating so slowly that one hemisphere is always turned toward the light, and the other always turned away. They don't spin, not like Earth does. They sway slightly, perhaps, nodding with gravitational tugs, but never turn freely. Instead, they face their stars like flowers frozen in a final bloom. This is not a rarity. It's a common outcome in close orbits. Many exoplanets, especially those circling small dim stars like red dwarfs, are locked this way, held fast by gravity, their days and nights stretched to the limits until time itself bends. What you end up with is a world divided, not just by light, but by temperature, by pressure, by habitability. A place where extremes rule, and where the only hope for balance lies not at the center of either domain, but at the edge between them. The Twilight Zone. It's an eerie phrase, borrowed from fiction, but here it means something real. A band of perpetual dusk circling the Terminator line, the place where day fades into night, but never fully commits to either. On one side of this line, the ground might boil beneath the unrelenting heat. Rocks crack, clouds vaporize, and the atmosphere churns in massive updrafts. On the other, ice builds layer by layer, air grows thin, and starlight never arrives. But in between, in the narrow zone where shadow meets fire, conditions might be just right. Just right for what? For air, perhaps. For water. For the gentle gradients that life needs in order to persist. If life ever did emerge on a tidally locked planet, it would likely cling to this ring of balance, migrating slowly as the planet shifts over long time scales, adapting not to days and nights but to gradients of survival. There would be no circadian rhythm, no sunrise, no sunset, only the eternal presence of a half-lit sky. And yet, the idea of stillness is an illusion, because these planets may not spin, but they breathe. Their atmospheres are dynamic, pulled and pushed by the ferocious contrast between the hot and cold sides. Winds whip from day to night at thousands of kilometers per hour, dragging heat with them. On some worlds, this constant flow forms massive jet streams, cyclones larger than Earth itself, and chemical storms that wrap the entire planet like ribbons of motion. The Terminator isn't a peaceful place. It's a place of tension, of movement, a borderland in constant flux. Imagine standing there, just inside the shadow. Behind you, a horizon cloaked in blackness, stars burning cold and clear. Ahead of you, the sky shifts toward gold, then white, then unbearable light. The star above isn't rising or setting. It's just hanging there, fixed in the sky, casting light sideways, like the edge of a knife. And because the planet doesn't spin, that sun burns down from the same spot in the heavens, day after day, century after century, never wavering. The ground beneath you might be baked hard from proximity, but the wind could be bitter with air rushing in from the cold side. It wouldn't feel like morning or evening, it would feel like both. Stretched into permanence, and that would be your world. Always a little too bright, always a little too dim, always balanced on the razor's edge of two extremes. Some planets like this may still have weather, not in the sense we know it, but in vast, planetary scale exchanges of heat, air rising in torrents on the hot side, spreading out in the upper atmosphere, then falling back down in freezing sheets on the dark side. The night might be filled with snowstorms made from exotic ices, or with silence, broken only by the sound of cracking crusts as frozen gases sublimate. Meanwhile, the dayside could be wrapped in a never-ending thunderstorm, lightning flashing through clouds of superheated vapor, driven by the constant, unrelenting energy of a sun that never moves. And yet, for all the violence, there is still room for calm. Some simulations suggest that if the atmosphere is thick enough, it can redistribute the heat, soften the contrast, make the twilight zone more than a narrow band, stretch it into a region where water could flow, clouds could form, and temperatures could remain stable over long spans of time. Not comfortable, exactly, but not impossible either. Not inhospitable. These are the kinds of places we look at now when we search for life, because red dwarfs are everywhere. Because many of the planets we've found in their habitable zones are likely tidally locked. Because Earth-like does not have to mean Earth-identical. It may mean something slower, stranger, a world with no sunrise, a world where every home faces the horizon. It makes you think differently about time. On Earth, we mark the passage of days by the turning of the planet. But what would time feel like on a locked world? Would you measure it by seasons? Slow shifts in orbit that change the angle of the star just slightly? Would you measure it by storms? By winds? Or would you simply stop counting? Would you learn to live not in cycles, but in permanence? There's a kind of peace in that, a strange stillness, a sense that the universe has found a different rhythm, not better, not worse, just alien. And yet, even there, in a world without rotation, there is movement, there is wind, there is light, there is the possibility of something watching the horizon, listening to the sky, waiting for whatever comes next, even if it never changes. For now they remain invisible. Hinted at maybe, suspected, but not confirmed. We've found thousands of planets orbiting other stars, some barely bigger than Earth, others swollen and bloated like miniature suns, but not a single exomoon, not one, has been seen with absolute certainty. They hide in the noise, drowned in the flicker of starlight, too small and subtle for the methods we've mastered so far. But they're out there. They must be. Because if there are planets, there will be moons. And if our own solar system is any guide, there may be more of them than planets by far. Around Jupiter alone, there are over 90. Saturn too. Small ones, lumpy and irregular, like captured fossils. Others smooth and round, shaped by their own gravity. Some so large they blur the line between moon and planet altogether. If these gas giants existed around another star, their moons might be the size of Mars, maybe Earth-sized, maybe more. Now imagine that not just here, but everywhere, tens of billions of planets scattered across the galaxy, and many of them giants. Many of those giants cradling entire families of moons. Icy ones, rocky ones, volcanic ones, layered with subsurface oceans, or cloaked in thick, strange atmospheres. If we could see them, we might find that moons outnumber planets, not just in count, but in habitability, in possibility. Because here's the strange thing. Moons may be better at supporting life than planets. Not all of them, of course. Not the dry, airless rocks. But consider Europa, Enceladus, Titan. Moons orbiting in the cold outer regions of our solar system, far beyond the traditional habitable zone, where the sun is just a pale dot in the sky. And yet beneath their surfaces, warmth persists. Liquid oceans, organic molecules, chemical gradients, the ingredients of life, simmering in darkness. What keeps them warm isn't sunlight, it's motion, tidal flexing, a dance of gravity between moon, planet, and sometimes other moons generates internal heat. It stretches and squeezes the core, like kneading dough, producing enough energy to keep water from freezing, to drive geology, to create cycles. It's an alien kind of warmth, hidden and quiet, but powerful. On Europa, that heat may keep an ocean deeper than Earth's from turning to ice. On Enceladus, it fuels geysers that spray into space, salty and rich with complex molecules. So what if this is common? What if every giant planet out there has moons like this? Dark oceans beneath frozen shells, warmed from within, protected from radiation, stable over billions of years. The surfaces may be cold, but life doesn't need the surface. It needs energy, chemistry, time. And those three things may be easier to find on moons than on planets scorched by flares or frozen in darkness. And if those moons are big enough, if they hold onto atmospheres, the story changes again. A massive moon around a gas giant in the habitable zone might experience day and night cycles, not just from its star, but from eclipses as it passes behind its planet. It might see twin sunrises, one from the distant star and another from reflected light off swirling cloud tops below. Seasons could be shaped by its orbit around the giant, adding layers of complexity to its climate. And if the gas giant has a strong magnetic field, the moon might be shielded from stellar radiation or bathed in auroras that crackle and dance endlessly in its sky. Whole ecosystems could adapt to that light, to those cycles. Trees, if there are trees, might grow in spirals. Creatures might learn to navigate the rhythms of two worlds pulling on them at once. There is a quiet richness in that image, not the violent extremes of hot Jupiters or lava planets, but a slow, deep stability, a place where life could grow in silence, evolve in darkness, thrive without ever knowing the sky. And when we search for signals, the chemical hints of life in an atmosphere, or the brief glint of artificial structure, it may not come from planets at all. It may come from one of their moons. That's the great irony. We've spent so long imagining alien civilizations on Earth-like planets, ocean worlds, yes, cloudy ones, rocky ones, but always planets. When the real cradles of life may be smaller, colder, more hidden, they may not orbit stars directly. They may orbit other worlds. And still, we haven't seen one. Not clearly, not yet. We have candidates, hints, a blip in a light curve that might be something more. Kepler 1625 b, for instance, a possible Neptune-sized moon orbiting a gas giant. Too big to be certain, too strange to be ignored. But confirmation takes time, and the instruments we've built were never designed for this. Still, it's only a matter of time. The telescopes being built now, and the minds turning toward this question, will make moons visible. And when they do, the galaxy may grow even richer, even more crowded, not just with planets, but with companions, with co-worlds, with orbits within orbits, complexity within complexity. The simple diagrams in textbooks will unravel into fractals, and in that unraveling, we may find a second genesis. Life, not on planets, but beside them. And that means something profound, because it means life might be far more common than we've dared to imagine. Not rare, not confined to a narrow belt of distance and warmth, but scattered like seeds. In ice, in salt water, in the twilight zones beneath frozen crusts, waiting, not for us, but simply existing in silence, in patience, in the orbit of something larger. There are places where spring never seems to end, where the thaw stretches on not for weeks, but for years, where buds emerge and stay open for a decade, never quite tipping into full bloom, never quite retreating into frost. These are not places of temperate predictability. or soft transitions. These are worlds where time itself feels warped, not by magic or myth, but by gravity, by geometry, by the cold mechanics of orbits and tilt. Alien seasons don't follow Earth's rhythm. They don't obey our familiar cycle of 12-month years and quarterly change. Some planets rotate so slowly that a single day outlasts a season. Others spin quickly but trace stretched-out paths around their stars, looping through heat and cold in long, uneven arcs. A few are tilted sharply on their axes, more than Earth ever dared, turning their poles into deserts or glaciers depending on the planet's slow nod through space. Imagine a world with a 40-year winter. Snow falls not in flurries but in generations. Lakes freeze thick enough to swallow forests. Entire species are born and buried beneath the silence of ice. The stars barely shift. The sun, if it's even visible, clings low to the horizon, casting long, blue shadows across endless fields of white. Time slows there, not metaphorically, but physically. A child might be born into twilight and come of age before the sun climbs fully into the sky. And then the change begins, but not like here, not with sudden warmth or a day that feels different. On a planet like this, seasons roll in like tectonic plates, slow, grinding, inevitable. Spring might take 20 years to unfold. Ice melts in patterns that look like erosion, not weather. Rivers return gradually, threading through valleys in silent determination. Trees, if they exist, wake up reluctantly, one ring at a time. Their leaves might take years to grow. Flowers, if they bloom at all, would be monumental events, flashes of color in a century of gray. And with that comes summer, blistering, radiant, oppressive in its longevity. Some of these planets tilt so drastically that one hemisphere faces the star for half its orbit. Decades of direct sunlight, decades of drought. On such a world, civilizations might migrate like nomads, chasing habitable zones around the curve of the globe. There would be no year as we know it, no reliable calendar, only the memory of cycles. Tales passed down from those who lived through the last autumn, the last solstice, the last true night. It redefines what it means to wait. On Earth, we prepare for winter by storing food, stacking firewood, insulating homes. We know it will pass. But what do you do when winter is a generation long? What culture grows in a place where the season you're born into is the only one you'll ever know? In such worlds, knowledge becomes legacy. The memory of rain, the texture of warmth. Those are stories, myths, inherited truths spoken by elders who still remember green. And not all of this is theory. Some of it we've already seen. There are exoplanets whose orbits stretch into ellipses so wide that their summers are scorchers and their winters are planetary exiles. Others are locked in complex gravitational dances with companion stars, tugged and tilted unpredictably over thousands of years. In some simulations, these shifts can plunge a planet into an ice age without warning. Not a geological epoch, but a seasonal one, swinging back only after centuries. On these worlds, adaptation looks very different. Life, if it emerges, must be either incredibly resilient or incredibly patient. It might burrow deep into soil or ice, waiting for the warmth to return. It might bloom explosively in short summers, only to retreat into spores or seeds, riding out the decades. Or it might evolve in rhythms so alien that we wouldn't even recognize them as cycles at all. No familiar rise and fall, no blooming and wilting, just slow transformation, mirrored in ice sheets and shifting winds. And the strangest thing is, this kind of world might be more common than Earth. Our neat, nearly circular orbit, our 23.5-degree tilt, our 24-hour rotation and balanced axial wobble. It's all remarkably stable, remarkably rare. Tilt just a little more, and the seasons swing wider. Stretch the orbit, and you change the tempo. Slow the rotation, and you turn climate into geography. Our seasons are the exception, not the rule. We are, once again, the oddity. So when we search for life, we have to change the question. We can't just look for Earth-like warmth or familiar calendars. We have to ask what life does when summer lasts 30 years. When rainfall is an ancestral memory. When daylight means decades of unblinking light, and night means silence so deep the air crystallizes. Would life migrate underground? Would it live only in oceans buffered by thermal inertia? Or would it simply slow down, sinking itself to the rhythm of a planet where everything takes longer? Even language might change. What would a poem sound like on a planet where a year spans a century, where the last rainfall came before your parents were born? Would you speak of weather in lineage, not forecast? Would memory stretch differently? Would grief? There's something beautifully strange in that thought, that entire biologies, entire ways of being, might be shaped not by the materials of life, but by its pacing, not just by what a world is made of, but by how slowly or quickly it moves through time. Alien seasons could last decades, and in those decades, life might take root not in spite of the slow rhythm, but because of it. It might learn to wait, to listen, to bloom only once, but magnificently. And when we look up at those distant stars and wonder what's out there, we may have to imagine not just different creatures, but different clocks, different hearts, beating slower, different minds, shaped by ages of light and cold, not less alive, just differently timed, far from the warmth of ordinary stars. In the deep dark where light folds in on itself, there may be planets, not orbiting suns, not basking in the slow comfort of starlight, but circling something far stranger, a black hole, a collapsed star so dense it has no surface, only gravity so strong that nothing, not even light, can escape. It sounds like science fiction, but in the quiet language of physics, it is possible. A black hole doesn't destroy everything around it, not indiscriminately. From a distance, it can be surprisingly tame. If you replaced our sun with a black hole of equal mass, Earth's orbit would continue, unchanged. The light would be gone, the warmth erased, but the path we follow through space, that elliptical thread we've traced for billions of years, would remain the same. That's the first truth to hold on to here. Black holes warp space, but they do not always devour. And so, yes, a planet could orbit one. Imagine such a world, suspended in a black sky, not orbiting a point of light, but a perfect absence. No glow, no heat. Only the strange halo of the accretion disk, if there is one. That spinning circle of gas and dust, compressed and heated into a furious ring of radiation. It wouldn't rise and set like a sun. It would hover, permanent and strange, a sideways smear in the sky, lighting the world in tones we can't even imagine. The day-night cycle would be meaningless. Light would come from the disk, not the object itself. And the color of that light would depend on speed, on temperature, on the tortured physics of matter falling toward the edge of forever. Blues, purples, X-rays invisible to human eyes. The sky might pulse, the horizon might warp, gravity would curve everything, and time would stretch. Near a black hole, general relativity takes the stage. Clocks tick slower, seconds pass like hours to an outside observer. To someone standing far away, a moment on this planet might take days, years, centuries. In some theoretical orbits, time could slow to a crawl. A civilization could rise and fall while their signals drift outward at a glacial pace. From Earth, their transmissions might be warped, delayed, echoing long after they began. But the planet itself would feel normal. Gravity is only strange at the edges. On the surface, assuming the planet was stable and far enough out, the pull might be no different than Earth's. You'd walk the same. You'd breathe, assuming there was air. You might not even notice the curve of time, not unless you left, but you would notice the sky. The stars would seem wrong. Not just dim or distant, but bent. Light passing near a black hole gets lensed, pulled into arcs, smeared like paint across glass. The night sky might look like it's spinning, not because the stars are moving, but because their paths are warped by gravity. Familiar constellations would twist into spirals. The moon, if there was one, might appear in more than one place at once. And yet, for all its strangeness, such a world might be quiet, stable, peaceful. If the black hole is isolated, not feeding, not accreting matter, it wouldn't shine, it wouldn't flare, it would just exist. A cold, invisible anchor. And the planet would follow its path, seasonless and dark, warmed only by internal heat, or perhaps by distant stars, whose rays arrive faint and delayed. Could life exist there? It's not impossible. If the planet retained enough geothermal energy, if it had radioactive elements or tidal forces to stir its mantle, there could be warmth. And where there is warmth, there can be chemistry. Life doesn't need sunlight. Not always. On Earth, we've found entire ecosystems under the sea, thriving in blackness, feeding on mineral vents instead of photosynthesis. Perhaps similar life, blind, resilient, patient, could arise in the shadow of a black hole. Maybe that's what makes these places so compelling. They're not just bizarre. They're conceivable. We've already found black holes with disks, some with companion stars, shedding material that spirals inward in glowing ribbons. Those disks radiate. They shine with the fury of friction and gravity. And in theory, a planet orbiting at a safe distance could catch some of that energy, not enough to thrive like Earth, but perhaps enough to survive. Enough for ice to melt, enough for clouds to form, enough for something to stir in the dark. And then there's the dreamer's thought. The what if. What if a civilization did arise on such a world? What would they see? How would they measure time? Would their myths revolve around the absence at the center of their sky? Would their science begin not with stars, but with shadows? Would they ever imagine that out beyond the void there are galaxies blazing with light, suns rising and setting in a sky that moves? Or would they believe they were alone, encircled by silence, cradled by a gravity they cannot see, their entire reality shaped by a thing that gives off no light, yet defines their days and nights? There is something haunting in that, and yet something beautiful, because these places remind us that stability doesn't always come with sunshine, that not all warmth comes from stars, that even in the coldest corners of space, the universe leaves room for balance, for rhythm, for worlds to take shape and orbit and wait. Planets can orbit black holes, and they might be waiting still. Light travels across impossible distances, across centuries of space and silence, across every empty gulf between stars. And in that light, there is information, not just brightness or color, but fingerprints, shadows, spectral riddles. Light can be caught, broken apart, sifted, and when it passes through the air of an alien world, it changes just enough to tell a story. We used to dream of touching other planets, of landing, sampling, breathing in their air to understand their essence. But now, we know we don't have to land at all. We just have to wait, watch. Listen in the language of photons. The method is delicate. A star burns, bright and steady. A planet crosses in front, a transit, from our point of view. And in that brief moment, some of the starlight filters through the planet's atmosphere, if it has one. That thin shell of gas, clear, invisible, maybe only a few kilometers thick, leaves its mark. Molecules absorb specific wavelengths. Hydrogen blocks one, methane another, water vapor, carbon dioxide, sodium. Each one interrupts the light in a signature way. So, we study the gaps, tiny dips in a spectrum, minuscule absences carved out of the starlight, like letters etched in flame. We stretch those dips across time, build graphs and models, and translate them into chemistry. From trillions of kilometers away, we are learning to read the skies of worlds we will never touch. The technique is called transmission spectroscopy, a poetic name for something so precise. It's not new, not really. We've used it on stars, comets, clouds in deep space. But to use it on planets, in no larger, real exoplanets, some no larger than Earth, some hundreds of light years away. That's recent. That's astonishing. That's watching the breath of another world from here. And the breath is strange. Some exoplanets have thick, puffy atmospheres filled with hydrogen and helium, left over from their formation. Others show signs of sodium or potassium, elements that tinge their skies yellow or violet. A few betray the presence of metal oxides, titanium vapor, even silicates. In the right temperatures, that means clouds of glass, rainstorms of stone, a sky unlike anything we've seen. Others are quiet, flat lines, no absorption at all. That could mean no atmosphere, a barren, silent surface. Or it could mean a heavy haze, a thick soup of high-altitude particles that blocks everything below. Sometimes what we learn is that we can't see. And even that tells us something. Some of the most exciting signs come from water vapor. Not oceans, not rain, not yet. But water molecules floating in the air. Water is a major goalpost, because where there's water, there might be clouds, rivers, lakes, life. We've found hints of water on hot Jupiters, on warm Neptunes, on giant planets, with temperatures too brutal to support life as we know it. But it proves the method works. And as instruments improve, we turn that sensitivity towards smaller planets, cooler ones, the kind that might cradle something alive. And then comes the dream, biosignatures. Chemical traces that suggest not just activity, but biology. Oxygen is one. On Earth, it's produced by life. Plants, algae, photosynthetic microbes. Alone, oxygen isn't proof. It can be made by light breaking apart water or other reactions. But combined with other gases, methane, for example, it becomes more compelling. A chemical imbalance. Something that shouldn't exist stably unless something's constantly producing it, breathing it, exhaling it. We're not there yet. We haven't found a definitive biosignature, but we're beginning to look. The James Webb Space Telescope, with its infrared eyes, has already begun scanning planetary atmospheres with more sensitivity than anything before. Others are coming. Missions like Ariel, LUVOIR, and the extremely large telescope, all designed to tease out the whispers in light. And it isn't just about transits. There are other methods. If a planet reflects enough light, we can analyze that too. Direct spectroscopy. It's harder, because stars are blinding. A planet's reflected glow is faint, dimmed by billions to one. But with the right tools, the right timing, we can isolate it. Catch the planet's dayside spectrum. Look for signs of reflection, absorption, cloud cover, even weather patterns. It's like seeing the color of a breath caught on a mirror. There are also thermal signatures. Light not from reflection, but from the planet's own heat. Some planets glow in infrared. Hot Jupiters, lava worlds, giant exoplanets still cooling from their birth. That thermal glow tells us about temperature, structure, circulation. A planet's heat is its own language, and again, it all comes down to light. We're not touching these worlds. We're not even seeing them, not directly. We're watching the way light changes when something invisible passes through it. We're decoding shadows, reading sunbeams, and the more we look, the more alien it all becomes. Skies of vaporized rock, air dense enough to crush steel, clouds of ammonia, methane, sulfuric acid, temperatures so high that molecules break apart and recombine mid-flight, atmospheres 300 times thicker than Earth's. winds that circle a planet every few hours, carbon worlds, sulfurous worlds, clear skies, red skies, greenish fog. Each one is a laboratory, a question, a possibility we hadn't imagined until light told us it was there. And one day, perhaps soon, the light will whisper something different. A spectrum with oxygen and methane together. A curve that suggests chlorophyll-like reflection. A shimmer in the data that no geology can explain. And maybe it will be faint. Maybe it will be debated. But it will mean that somewhere out there, another planet is breathing in a way that seems familiar. Breathing like us. Not just rock and gas, but home. For now, though, we keep watching. We wait for the transits. We collect the light. We read it like an ancient script written in fire and distance, each line a fragment of a story still unfolding. The universe doesn't hide its secrets. It beams them to us, gently, in the quiet shimmer of starlight. Some planets are vanishing, not in a moment, not with violence or finality, but gradually, in whispers, losing themselves atom by atom, their skies pulled upward, outward, into space, until the planet is cloaked in its own unraveling. It begins with proximity, a world caught too close to its star, where light is not just warmth, but force, where radiation doesn't stop at the atmosphere's edge but pushes through it, cracks it open, and takes pieces with it. These are not subtle stars. They flare, they seethe. Their ultraviolet light sears, their winds buffet. And for planets that orbit too near, especially those with light, gaseous atmospheres, the consequences are slow erosion. Every day, the upper layers of their air heat and expand, lifting into space like steam from boiling water. At first, it's only a shimmer, then a haze, then a long, ghostly tail. A planet becomes a comet. We've seen it, not just inferred or modeled, but seen in light. In some systems, the transits are asymmetrical. The planet doesn't just pass in front of the star and dip the light smoothly. Instead, the light fades early or lingers late. It flickers oddly. The shape of the shadow is skewed, stretched, like something is trailing behind. That's the atmosphere, already gone from the planet's surface, still catching the starlight as it drifts away. One of the first examples was a planet called HD 209458b, an enormous gas giant orbiting close to its star. Too close. Its year lasts just a few Earth days. Its atmosphere, rich in hydrogen, was seen to swell out far beyond the planet's radius, a vast, bloated shroud. Ultraviolet observations showed the hydrogen escaping, forming a massive tail, tens of thousands of kilometers long. The planet itself was still intact, but it was bleeding into space. And there are others. GJ 436b, another hot Neptune, has been observed with a similar tail, so large that it dims its star long after the planet itself is gone from view. The tail is shaped by stellar wind and radiation pressure, a ghostly plume pushed backwards like a streamer in solar breeze. It's easy to imagine these worlds as doomed, but that isn't quite right. This is not destruction in the way we think of it. It's more like transformation, shedding. Not all the mass is lost. Not all the atmosphere escapes. Some planets may stabilize. Others may change category entirely. A mini Neptune could lose enough gas to become a rocky super-Earth. A gas giant might shrink into a stripped core, all atmosphere gone, revealing a metallic skeleton of what it once was. These remnants, often called Chthonian planets, are like the bones of worlds, dense, exposed, weatherless. Survivors not because they withstood the heat, but because they gave into it, offered themselves piece by piece until only the core remained. It raises strange questions about planetary evolution. What we see today may be only one phase in a planet's life. Some rocky planets might not have formed rocky at all. They could be the exhausted remnants of larger, puffier ancestors, reshaped by time and radiation. Our categories: rocky, gaseous, icy, maybe just moments in a longer narrative. A story told through loss, and it happens more than we once believed. Stars, especially young ones, are active. Their flares and outbursts can be ferocious. A planet caught in those early years is vulnerable, especially if it's small, especially if its gravity is weak, especially if its magnetic field is absent or fragile. Without protection, even an Earth-like world could be scoured clean. Atmospheres aren't permanent. They're gifts, delicate, shifting, borrowed. Even now, Earth loses atmosphere. Tiny amounts, constantly, to the solar wind. But our planet is large enough, and our magnetic field strong enough, to hold most of it close. Other worlds are not so lucky. Mars once had rivers and seas. Now it has a thin, cold atmosphere, and a surface dry as dust. It didn't vanish in catastrophe. It faded. Over millions of years, sunlight and wind peeled it back. Now, imagine a planet even closer to its star than Mercury. Imagine no magnetic field, a smaller mass, a star 10 times more active than our sun. That's not just erosion, that's exhalation, an entire world sighing into space. Some exoplanets are in the middle of that sigh. We catch them halfway, not as they were or will be, but as they are, dissolving. In data, they appear strange. The light curves are off. The temperatures are uneven. The compositions, when we can read them, are skewed toward elements that shouldn't dominate. Metals, silicates, ash. It's as if we're seeing the bare skin beneath the makeup. The planet stripped to its essence. And sometimes, it's more than air that's lost. There are theories, not yet confirmed, that on certain lava worlds, material from the surface itself may be vaporizing. The rock boils. The elements rise, become gas, and escape. Sodium, iron, even calcium. These aren't just atmospheres bleeding away. These are landscapes unraveling. We don't know how long such planets last. It depends on mass, distance, stellar activity. Some may only lose a fraction of themselves and stabilize. Others may vanish entirely, leaving only dust and memory, a warning written in evaporation. But they are beautiful, not just tragic or strange, but beautiful, because they show us something fragile and dynamic. Planets are not static marbles in space. They breathe, they change, they burn and weather and drift. Some are born, some collide, some get thrown from their stars, and some simply fade, one particle at a time. Even in loss, they glow. They leave trails, not just of gas, but of insight. We follow those trails backward, trying to imagine what the planet once was. We follow them forward, wondering what might be left in a million years. And as we do, we learn more about survival, about thresholds, about balance and imbalance. Every vanishing planet maps out a new boundary in what's possible, a new edge to the territory of existence. And still, across that vast canvas, the light comes, the trails shimmer, the stars pulse, and somewhere out there, another ghost is forming, drifting in the sun's embrace, quietly letting go. Some planets are old, not just ancient in the way we think of fossils or ruins or weather-worn stone, but truly old, older than Earth, older than our sun, older than many of the stars that now light the sky. They were born when the galaxy itself was young, when stars were forming in dense clouds untouched by heavy elements, when there was less to build with but still enough to craft a world. These planets have witnessed time on a scale we can't easily hold in our minds. They have orbited through epochs. They have outlasted stars. One of the oldest known exoplanets is called PSRB, 1620-26b, a name that gives no hint of its ghostly story. It orbits not a single star but a pair, a white dwarf and a pulsar, both stellar remnants, both the afterlives of suns. This planet is estimated to be around 12.7 billion years old. Earth, by comparison, is just 4.5 billion. That means this planet is nearly 3 times older. It formed when the universe was just beginning to settle, before the Milky Way had fully formed, before Earth was even possible. It circles its strange, dead stars in a globular cluster, a crowded, ancient neighborhood of tightly packed stars that orbit the galaxy like a halo. These clusters are fossils too, some of the oldest structures we know. To find a planet there is astonishing, because it means planet formation began almost as soon as stars did, long before the periodic table was rich with metals, long before supernovae seeded the cosmos with the ingredients for complex chemistry. And yet, somehow, even then, a planet formed. But what does it mean to be a planet that old? Not just chemically or geologically, but experientially. A world that has seen suns rise and fall not once, but many times. A world that's endured changes in its host system so extreme they would seem apocalyptic to us. A planet that has kept orbit even as the stars it circled died and collapsed. What would the surface of such a world remember, if rock could carry memory? Perhaps once it had warmth, a young, stable star, atmosphere, water even. Perhaps for billions of years it was calm, and then its sun expanded, aged, shed its layers, and collapsed into a white dwarf. The light changed, the climate shifted, the skies fell quiet, but the planet remained, and it's not alone. We're beginning to find more of these ancient worlds. Some orbit stars that are already old themselves, stars that formed when the universe was less than a third its current age. The planets that circle them are not all small or dead. Some are giants. Some may be rocky. Some might still have atmospheres, oceans, weather. Some might still be active. Others may have once been more than that. Because when you have billions of extra years to work with, everything stretches. Evolution, development, collapse. Life, if it ever arose on those worlds, would have had time not just to emerge, but to thrive, diversify, decline, vanish, and perhaps rise again. On Earth, life has only had a few billion years to get this far. On those planets, there could have been entire cycles, civilizations not just lost, but fossilized and eroded beyond recognition. Ruins ground to dust long before Earth was born. Or maybe life never took hold. Maybe the early universe was too harsh, too chaotic. Maybe these planets are sterile and always have been. But even that tells us something. It shows us the conditions that failed, the ingredients that weren't enough. Each ancient world is a data point in the long equation of life, a control group in the grand experiment of existence. And they're not just frozen relics. Some may still be changing. A planet older than Earth doesn't have to be dead. Tectonics can continue. Volcanism, magnetic fields. If it has a moon, tides might still stir its oceans, if any remain. If it orbits a stable star now, it might have settled into a kind of second act, a long twilight rich in chemistry. Or, if it's drifted close to a hotter star later in life, it could be undergoing a dramatic rebirth, its surface transformed, its atmosphere reignited. Time doesn't move evenly in space. Gravity stretches and slows it. Radiation alters it. But the raw numbers remain. Some planets have had 5 or 6 billion more years to exist than we have. That's not just time for geology. That's time for philosophy, for mythology, for memory so deep it becomes indistinguishable from instinct. If minds ever formed on those worlds, they may have experienced time in ways we can't grasp, not because of speed, but because of abundance. And yet, here we are, past, new, by comparison, still spinning in our early years, still sorting out the basics, looking outward, reaching with telescopes and instruments for light that left those ancient planets long before our oceans formed. When we study these old worlds, we're not just studying planetary formation. We're studying patience, endurance, the long tail of possibility. What emerges over 10 billion years? What withers? What persists? We often frame the search for life as something forward-looking. What will we find next? What might be evolving now? But these planets ask another question. What might have been? Not science fiction, but science history. A prehistory of life that we'll never see, only infer. Ghost stories written in orbital mechanics and elemental ratios. They are reminders of cosmic humility, that Earth is not the beginning, that the story of planets, and maybe of life, has been unfolding far longer than we've been watching, and that we are latecomers, arriving just in time to catch the echoes. Somewhere out there, in the dim halo of the galaxy, or the quiet corners of ancient clusters, those old worlds still turn. Dusty, silent, persistent. They orbit, they remember. We are at the beginning. Not metaphorically, not poetically, but factually. Standing at the very edge of knowledge, peering out into a sky full of secrets we've only just begun to hear whisper. Just 3 decades ago, the idea of planets beyond our solar system was still unconfirmed, still the subject of speculation, not certainty. For all the thousands we've now cataloged, the millions we suspect, and the billions we estimate, the truth remains quietly humbling. We've barely scratched the surface. Most of what we know comes from light. Not pictures, not colors, not even shapes, but shadows. Faint dips in brightness, subtle wobbles, a photon delayed, a spectrum ever so slightly skewed. From these echoes, we've begun to map alien worlds. But this is a language we are just learning to speak. The vast majority of planets, the small ones, the cold ones, the quiet ones, remain invisible to us, not because they're too far, but because we don't yet know how to see them. We live in a narrow moment in scientific time, past the point of ignorance, but still a long, long way from understanding. The tools we've built, Kepler, TESS, James Webb, are only the first instruments of a long symphony. They've opened the curtain, but the stage is still dark. The coming decades will bring instruments that can not only detect planets, but image them, not in the abstract, but in the direct. Pictures of weather, of land masses, maybe even oceans. The lines between astronomy and exploration will blur. We won't just discover, we'll visit, and with that, something will shift. Because right now, wonder is the tool we use most. It fills the space between data points. It makes meaning out of scarcity. We imagine, because we must, what we cannot yet observe. When we hear that there are planets of diamond, or lava, or glass, it's not because we've flown there. It's because the light suggested it, faintly. When we speak of rogue planets drifting through the void, we haven't watched them pass. We've done the math. We've listened to the silence and heard footsteps anyway. There is power in this kind of wonder. It's what builds telescopes. It's what writes algorithms. It's what drives generations to ask better questions than the ones before. It's not empty speculation. It's fuel. A quiet, persistent desire to know more. Still, there is humility in the air of this moment. Most stars we see with the naked eye are already known to host planets. But for every one we've confirmed, there are tens of thousands we haven't. Most planetary systems are still hidden, cloaked by distance, drowned in starlight. We suspect there are trillions of exoplanets in our galaxy alone. Of those, we've found just a few thousand. And the ones we know best? We still know poorly. A planet might pass in front of its star once every few days, and we'll catch it, if our instruments are aligned and our timing is right. But we rarely see more than its size, its mass, its orbit. Sometimes we glimpse its atmosphere. Sometimes we can guess at its temperature. But the rest, its surface, its storms, its secrets, remain unspoken. That's the scale of our infancy. Each planet is a locked room. We've only found the keys to a handful, but we are learning, and in the learning, we're beginning to see how wildly different these worlds can be, how unpredictable. They don't follow the rules our solar system taught us. They orbit in searing proximity. They drift alone. They spin in strange rhythms. They form in places they shouldn't. They break our models, and then ask us to write better ones. Every new discovery isn't just a new planet. It's a revision, a note in the margin of the textbook we thought we'd already written, and this is just the start. A century from now, we may look back at this era the way we look at maps drawn before the continents were known. Not wrong, but early, full of dragons and guesses and beautiful mistakes. We may smile at how many planets we missed, at how certain we were about things that turned out to be incomplete, and we'll be grateful, not embarrassed. Because this is how knowledge grows, in pieces, in echoes, in leaps that start with stumbles. There will come a time when we find a planet and know it has rain, when we can say it has clouds, forests, even creatures. And that moment, when it comes, will not be an ending. It will be a beginning, too. A wider beginning than this one, because then the question won't just be, what's out there? It will become, who's out there, and what are their stories, and how long have they been waiting for us to notice? For now, we wait in the dusk before that dawn. We listen. We imagine. We build. We look up with instruments and hopes alike. We've barely begun, but we've begun, and that, in itself, is extraordinary.